Okay, a little bit about center of mass. Imagine we got two particles, two point masses, M1 and M2, at positions x1 and x2 along an axis. So the x-axis is this way, and we have here a light support. Now it's like a very light meter stick, but strong enough to support the two masses. Now, that object actually has a center of mass itself. Okay? And you're going to see how to handle that. It's pretty easy. But we're going to assume it's so light that its center of mass doesn't have any big influence. Okay, well, book gave you a formula and then explored the formula for the mass spring program. Okay? Gave you a formula for center of mass and asked you to do things with the formula. And it was a good, sophisticated introduction to center of mass. And I like what they did. I don't remember seeing anything in the problems that told you how you would find the center of mass by balancing. Okay? As I just showed you with the meter stick. The center of mass is the point at which there's balance. Center mass is a balancing point. And the balancing point has the okay, let's say that center mass is at x bar. Then M2 times this distance has to equal M1 times this distance. Or we could put it this way. The reasons that are coming up, intuitively we think of this mass as tending to make the system rotate in this direction. Well, that's the negative direction of rotation. Positive direction of rotation takes the x-axis toward the y-axis, not the x-axis toward the negative y-axis. So the rotational effect here is M2 times x bar minus x2. X bar minus x2 in this case would be negative. That would be a negative rotational influence, a negative torque. Now, this is intuitive, but we make it more precise here in a couple of weeks. Okay? This one gives you a positive torque because it tends to rotate you around this way in the positive direction. And you get that by multiplying M1 times X1 minus X bar. Okay, so there's the equation. Another way of saying it is the rotational influence of this equals the rotational influence of this. And I don't think I wrote that down correctly. It's not equivalent. It's equivalent to this. This is negative, this is positive, they add up to 0. Well, anyhow. That's what it comes down to. This is equivalent and you can show that it's equivalent just by rearranging these terms. Just solve for x bar. And that's where it comes from. Thus, you take the derivative of both sides, and it's not x1 plus x2, it's m1 plus m2. Just follow the rules for derivatives. Derivative of this thing is just, well, the only terms of the m1x1, the m2x2 that are changing, okay? With time, assuming the masses aren't changing. If the masses are changing, then the derivative gets a lot more complicated. You got quotient rule with chain rule and all kinds of interesting stuff. And you sometimes need to do that. But right now, this is all you need to do. So this is just straightforward application of derivatives. I'm not sure that the mastering have to actually understand that. Okay, don't think it maybe was required to understand all the problems, but that's writing in the notation I prefer to use. That's the velocity of the center of mass. V sub x bar, velocity of the center of mass. And if you take another derivative, the derivative of this with respect to t, we're going to get derivative of v1 with respect to t, which is just the acceleration. And derivative of v2 with respect to t, which is the acceleration of v2. Acceleration of v1, acceleration of v2. That gives you the formula that you use to solve these problems. Everybody seems to solve most of the problems, but that's what's going on. Okay, so wanted to show you that. Wanted to show you the intuitive thing about center of mass, balancing point. If you know, you and an 8-year-old kid are standing on a 2x6, where do you balance it? Closer to you than to the kid, right? Take that intuitive result, get the idea of torque, which is just the distance times the mass with the direction of rotation, okay? You get this, and that's where this comes from, and then you take derivatives and you get the formulas that you've been using. Okay. I also talked about external versus internal forces. These masses attract each other gravitationally. There's not much attraction, but that's an internal force. Okay? It's a force exerted by the particles of the system on one another, as opposed to a force exerted by something external to the system, something that isn't one of the particles, exerting a force on the particles. Okay? Or if these are charged, because you electrically charge them and get a significant force between them, and if they're movable, they'll either be repelling each other or attracting each other. Okay? Well, those are internal forces, and it turns out that the accelerations that you get, the greater mass will have a lesser acceleration because the forces are equal and opposite. And that'll go together to ensure that the center mass doesn't change. Now, you work through details of that sort of situation, but that's a typical situation. You got two things that are attracting each other, or maybe there's a rubber band between them. You release the rubber band, they move together, their center of mass doesn't change. We could actually do that on a meter stick. We could balance two cars. Of course, it'd be hard to get them to stay on the meter stick. We balance two cars, use magnetic attraction, use a rubber band, a spring, exerting equal and opposite forces in the cars. We could balance the thing and then release the system as the cars approach, or if you have a repulsive force as they move apart, center mass is not going to change. The balance is going to remain. So that's something you really want to try to understand. And also, that illustrates an internal force. The force that is exerted equal and opposite due to their positions, okay? Or whatever. Equal and opposite forces they exert on each other don't affect the center of mass, even if they're moving.